Today, what I want to cover is doing a few examples on limits involving trig functions, so a bit more challenging ones, and then we'll continue with it, okay? Let's go. So example, limit as x approaches 0, let's say sine of 3x divided by sine of 4x. So well, first of all, what I'm going to do is I'm going to plug in the 0. So I get sine of 0 is 0. And on the bottom, sine of 0 is 0. Okay? And remember that what we know and what we proved, so we showed that the limit as x approaches 0 of sine x divided by x is 1. This we showed that using the squeeze theorem. Okay, so that's what I'm going to do. So I need to be able to recognize this pattern in here. Okay, let's do it. So I'll do the first one right away, and I'm going to give you time to do the second one. So equals limit as x approaches 0 of sine 3x over sine 4x, and I'm going to divide the top and the bottom by x. Okay, that way I have limit as x approaches 0. So on top I have sine 3x over x, and on the bottom I have sine 4x over x. Okay, now what I'm going to do is I'm going to put the limit on top and limit on the bottom. So I have limit x approaches 0 sine 3x over x, and on the bottom limit x approaches 0 of sine 4x over x. Okay, so now I have two limits to evaluate, the top one and the bottom one. And this we know how to do. We've done this last class. So I know that I'm going to multiply here by 3, top by 3, and here I'll multiply by 4 and top by 4. Equals. So in the top, I could extract a 3. 3 times limit x approaches 0 of sine 3x over 3x. And on the bottom, I could extract a 4. Limit x approaches 0 of sine 4x over 4x. Okay, you following me? Okay, now this, we recognize this pattern. So this is 1. And this also, same thing, this is 1, right? It's sine of 0 over 0, and the argument of sine and the denominator are the same, so this is 1. That's it. So my answer is just 3/4. Okay, don't do on the test, don't just go and pull out a 3 and pull out a 4, because you're going to get 0. Because that's not why the answer is 3/4, because of all this.
Sir?
Yep.
Can I just take the derivative of the numerator and the denominator?
Who was asking this?
The one.
Okay, did you already take the course?
Yeah.
Oh, okay, so that's why. So you're using, what are you using here?
L'Hopital's rule.
Yeah, L'Hopital's rule. So for L'Hopital's rule, we have to know that L'Hopital's rule, what it is, and you have to know how to do derivatives. And so that's, for now, you cannot do this because, right? But eventually, yes.
Okay, thank you.
Okay. Okay, any questions on this?
At the top, when you started it and you divided both of them by x, where'd you get that x from? Like, how do you know you could do that?
First of all, I could always divide divide or multiply by anything I want on top and bottom. It doesn't change my fraction. So I'm allowed to do this. That answers why am I allowed to do this. Now, why did I choose x? That's another question. Why did I choose x? It's because I want to get as close as possible to recognizing sine x over x.
Okay, thank you.
Okay, so go ahead and try one now. Okay, so try one right here. So same type. Okay, so no using L'Hopital's rule yet. Okay, so sine 5x over sine 7x. Okay. All right, go for it. Okay, let's do it. First thing we do, we verify that it's, if I plug in 0, what happens? So I get 0 over 0. And again, same process as we did right here. So it's equal to limit as x approaches 0 of sine 5x divided by sine 7x, divide the top and the bottom by x. Okay, and so equals limit x approaches 0 and one big fraction sine 5x over x over sine 7x over x. Then I'm going to put everything on one big fraction and I'm going to distribute the limit inside. Limit x approaches 0 sine 5x over x divided by limit x approaches 0 sine 7x over x times 5 and times 5. So I could just, the 5, I could put it right away in front, okay? And same thing here, times 7 divided by 7. So I'm just gonna take the 7 outside of the limit right away. Okay, and now this is 1, we know, and this limit is also 1, we know. So my answer is 5 over 7, like we all got, pretty much. Okay, any questions? Okay, let's move on to something a bit more complicated, okay? Let's try one right away. Let's try this one. So x approaches 0, so try sine squared of 4x divided by sine squared of 5x. Okay, so now I have a sine squared. Do you want to try it or you want me to do it right away? No answer? So maybe no, you want to try it? Okay, try it. Go ahead.
Yeah, let us try it.
Okay, try it. First thing we do, as usual, plug in the 0. So I get sine of 0 squared is 0 divided by sine of 0 squared is 0 as well. Okay, so equals limit x approaches 0. So what did you guys do? You divided by what? Top and bottom. No? You divided by, no, that's not good. You told me x, that's not good. What do you divide by, top and bottom?
You put everything in squares?
You put everything in square, also everything power 2?
Yes.
You could do that. Take out the power? No, you can't take out the power. No, I'm getting weird answers here on the chat.
Is it correct if I divided by x squared?
Yeah, very correct. Okay, so there's two ways to go about this one. You could either divide top and bottom by x2, that's very good, like you just said. Or what you could do is you could put everything to the power of 2 also. Okay, both ways work. Okay, I'll do both ways. You know what? I'll do both ways. It's good exercise to do it both ways. So first way I could do is go like this, divided by x2 and divided by x2. Or, okay, I'll do a second way here. I'll do it on parallel on this side. I could go limit x approaches 0 of sine 4x over sine 5x, all this to the power of 2. Okay, and here if I insert the limit inside, the inside becomes the same problem as the one we just did. Okay, so that's maybe easier. Okay, but whatever, it's the same thing. So let me continue this way, left side first.
Sir,
Yes,
can I separate it instead?
can you, I'm sorry?
Can you separate it like, can you do sine of 4x times sine of 4x over sine of...
Also, very good, yeah, also. This ends up being the same thing as this. You're
Okay.
saying the same thing as this. Yeah, you're right. Okay, so here we have limit as x approaches 0, and so on top I will have sine squared of 4x over x2, and on the bottom I will have sine squared of 5x over x2. Good. And then I will put the limit inside. So it's limit as x approaches 0 of sine squared 4x over x2, and on the bottom limit x approaches 0 of sine squared 5x over x2. Okay, so far? And then here, you remember, I put everything to the power of 2. So I think you're better off with this method, will be faster. Okay, so we have on top limit x approaches 0 of sine 4x over x, all this squared, and on the bottom limit x approaches 0 sine 5x over x squared. Okay, and then you remember times 4 and times 4, and here times 5 and times 5. Okay, so notice how I pull out the 5 out of the limits I'm allowed. Okay, and then I'm going to take it out of the square, and then it's going to become 25. I'll take it out of the square, it will become 16. Okay, and this of course is 1, and this of course is 1. So the answer will be 4 squared over 5 squared, and that's why it's 16 over 25. Oops, you can see, I think, sorry. There you go. Okay, and in the while you copy, I'm going to do the second way here. So, of course, inside now I'm going to divide by x. So limit x approaches 0, sine 4x over x, and on the bottom, limit x approaches 0, sine 5x over x, times 4 times 4 times 5 times 5, all of that squared. And so I skipped right away to this, pretty much this step. Okay, so the answer is 4/5 power 2, which is 16 over 25. So this way is pretty much shorter. Any questions before I go to something a little more difficult? Okay, you done writing? Does anybody need more time to write? Okay, so let's continue. So let's go with something a little more complicated. Limit x approaches 0, 1 minus the cosine of 3x divided by sine squared of 2x. Okay, what is the first thing that we do?
Plug in 0.
Very nice. So I plug in 0 on top. So cosine of 0 is 1. 1 minus 1 is 0. So the top is 0. And the bottom, sine of 0 is 0. Okay, so I have my undetermined form. So what do I do now? I'm taking suggestions.
Divide by x.
Is an identity.
Okay, what's the identity?
It's 2 sine x times 2 cos x.
2 sine x. Oh, you mean for the bottom? No. Maybe the bottom you could 2 sine x cos x, okay. But I don't think it will help you here. Okay, so let me do the first one. Okay, unless you want to try, but I'll do the first one and then I'm going to give you one to do on your own, okay? So equals to limit x approaches 0, so 1 minus cos of 3x divided by sine squared of 2x. And what I'm going to do here, and this is a pattern that you will recognize often, when you have 1 minus cos or 1 minus sine, it's very practical to multiply by the conjugate. 1 plus, just like we did with square roots, okay? So multiply the bottom as well by 1 plus cos of 3x. Okay, and you will see what's going to happen now. Equals limit x approaches 0. So here we go. So 1 times 1 is 1. Then 1 times cos 3x, so it's plus cos of 3x. Then minus cos times 1 is minus cos of 3x. Then minus cos times plus cos is minus cos squared of 3x. Okay, and then on the bottom, sine squared 2x times this stays 1 plus cos 3x. Okay, so this is a rule. Whenever you can, you keep the denominator factored. You never want to open up the denominator. Okay, you develop the top, but the bottom you never develop because you want to hopefully simplify something. Okay, so never open up the bottom, keep it factored. This is why I did not multiply inside. Okay, so obviously I'm going to cross out the cos, 3x minus cos 3x, and then I'm left with what? Limit as x approaches 0 of 1 minus cos squared of 3x divided by, and the bottom stays, sine squared of 2x times 1 plus cos of 3x. Okay. We went a bit, we advanced a bit, but now what?
1 minus cos squared is equals to sine squared.
Very nice. Okay, so from the identities that we did a few classes ago, okay, if you remember that sine squared x plus cos squared x equals 1, right? We extracted this identity from the unit circle. We did it together. And so if I isolate sine squared, x is going to be 1 minus cos squared x. Okay, it's very good. Therefore, here I recognize 1 minus cos squared, so this will be sine squared. That was the whole point of multiplying by the conjugate, to get this form so I could have a sine. So it's equal to limit as x approaches 0. So the top now is sine squared of 3x. And then on the bottom, I have sine squared of 2x times 1 plus cos 3x. Any questions until here? Okay. We're almost done. So it's equal to, I'm going to separate the limit into two parts. The first limit, limit x approaches 0 of sine squared 3x over sine squared of 2x times, and then the second limit, I will take care of this guy, which is going to be 1 over 1 plus cos of 3x. Okay, I did not change anything. Any questions?
How did you get that?
This last step.
Yes.
Okay, so this is like times 1, right? This is like times 1. So this over this times 1 over that. Right? This over this times 1. And then I just apply the limit on each of the terms, of the factors. Is that okay?
Yeah.
Okay, so let's see. I have two limits to evaluate here. Well, this one is pretty easy, because if I plug in 0, I get cosine of 0 is 1, 1 plus 1 is 2, so this is 1/2. That's easy. Okay, so this one, I'm just going to write 1/2. Now this one, I know how to do, I just did one. The last example we had was a sine squared over a sine squared. So we do the same process as before. Okay, so I'm going to go a bit faster for two reasons. First is because we just did it, and second is I don't have much space in the paper. So I'm going to skip a bit of steps, but if you need, you'll look at the video and you'll go back to the last question. You'll see. Okay, so it's equal to sine 3x over sine 2x, limit x approaches 0, all this squared times, and this is 1/2. Okay, so I will divide here by x, and I will divide here by x.
Why is it 1/2?
Why is this 1/2?
Yeah.
So this you don't understand is half here.
Yeah, like I don't understand that.
Okay, so plug in 0 here. 3 times 0 is 0. Cos of 0 is 1.
Okay.
And 1 plus 1 is 2.
I get it.
Okay.
Thanks.
Okay, so now we have equals. So on top, I will have the limit as x approaches 0, sine 3x over x, and the bottom limit x approaches 0, sine 2x over x. All this to the power of 2, all this times 1/2. Okay, and then I will do times 3 times 3 times 2 times 2. Okay, and that's it. This will be 1. This will be 1. So I have 3 over 2 squared times 1/2. Okay, that's pretty easy. So the answer will be 9 over 8. This is what I get. questions?
I have a question.
Sure.
In the beginning, we have 1 minus cos squared 3x.
Yes.
Could we have used the same process with, for example, sin squared when we multiply? We first divide it by x squared and then multiply both sides by 3, taking the first 3 out to the limit, and the second 3 stays in the bottom. So we have 1 minus cos squared 3x over 3x, which gives us 1.
Who says it gives you 1?
It's the identity, no?
No, I don't know this identity. What? 1 minus cos 3x. 1 minus cos. You're talking about this step here?
Yes.
Okay. So you're telling me 1 minus cos squared 3x over 3x, that's 1?
3x squared.
No, it's not good. It's not good. 9x squared would be good. 1 minus cos squared 3x over 9x squared, this will give you 1, yes. But not 3, because everything is squared. Okay, that's why you really have to be careful and go through all the steps. Okay, you can't start to try to find shortcuts right away. Okay, does this answer your questions or no?
Yes, thank you.
Okay. So Carlo, you have a question. Why is it 1/2? Did I answer you already, or was it someone else? Or was it you? Okay, I did. Perfect. So you guys want to try one maybe? Okay, try one like this, and I'll give you. If you get the next one right, I'll give you one more example, and then we'll go to continuity. Okay, which is the last section before we start derivatives, which hopefully we'll do next class. But if I understand correctly, next week we don't have class on Monday, and Tuesday is a Monday schedule, right? Is that right?
One of our teachers said it's not that, but the calendar says it is.
The calendar says that it's a Monday schedule, right?
Yeah, but I have a teacher who said it wasn't that. I'm not sure.
Okay, I think I want to go with what the schedule says. Tuesday schedule. You stick to it. There's a new calendar. Okay, I'm not aware of this. Okay, thank you. I will double check anyways. Okay, so let's try. You try one, okay, on your own. So limit as x approaches 0, let's say 1 minus the cosine of 5x divided by the sine squared of 3x. Okay, let's go try it on your own, okay? I'm giving you, first thing we do, as usual, plug in 0 here. 0 over 0, perfect. And let's go. I see that you guys are getting the hang of this. So I'm gonna go a bit faster. So 1 minus the cosine of 5x over sine square of 3x. I will multiply by the conjugate. 1 plus cos 5x, 1 plus cos 5x equals limit x approaches 0. So if you factor, you simplify the top, you develop the top, you will get 1 minus cos squared of 5x after simplifying. And on the bottom, I will have sine squared 3x times 1 plus cos of 5x, which is limit x approaches 0. So the top is going to be sine squared 5x. The bottom will be sine squared 3x times another limit for the remaining term, 1 over 1 plus cos of 5x. Okay, then we said we put everything so limit I don't want to skip too many steps, so I won't. So limit x approaches 0, sine 5x over sine 3x, all this to the power of 2 times, and this, remember, again, this is still 1/2. Okay, then I'm going to divide the top by x and the bottom by x. Nothing changed. And then here, I will multiply by 5 top and bottom. And here I will multiply by 3 top and bottom. And then distribute the limit inside. So I have 5 times limit x approaches 0 of sine 5x, sorry, over 5x. And on the bottom, 3 times limit x approaches 0 of sine 3x over 3x, and all this to the power of 2, and all this times 1/2. And that's it. This is 1, this is 1, and we have 25 over 9 times 1/2, so it's going to be 25 over 18, which is what most of you guys got right.
I have a question.
Yes?
Can we just, do we have to write the second to last step?
This one here?
Yeah.
Or you want to go from here to here? You mean the fact that I pulled out the 5? No, it's okay. I would accept that.
Okay, thank you.
Okay. Okay, I can move on. All right. Let's go. Last example, and then we'll go to continuity. So show that the limit as x approaches 0 of 1 minus cos x over x is equal to 0. Okay, so this was the second identity that I showed you, right? I said there were 2 identities. The first one we proved sine x over x equals 1. We proved it using the squeeze theorem. And now this one, given all the examples we've done, try to show me that this is equal to 0. Okay, so try it. So limit x approaches 0, 1 minus cos x over x. So of course, if you plug in 0 here, you get 0 over 0. So I will multiply by the conjugate, 1 plus cos x, and on the bottom, 1 plus cos x equals limit as x approaches 0. So on top, what do we have? 1 minus cos squared x, and on the bottom I will have x times 1 plus cos x. Is that okay, everyone? Okay, and 1 minus cos squared x, we know now that its limit of this will be sine squared of x, and on the bottom I will have x times 1 plus cos x. Questions? Okay, I will divide, like separate the sine squared into sine x times sine x, and separate the limit into 2. So this will be sine x over x times, and the other fraction will be sine x over 1 plus cos x. So I did not change anything. Okay, the top is still sine squared, and the bottom is still x times 1 plus cos x. It's still the same thing. The only thing I did is I distributed the limit. Okay, and this is very convenient because now this is 1, and this is 0. If I plug in 0, I get 0 over 2, which is 0. And so 1 times 0 is 0, and I'm done. Okay, any questions?
Sir,
Yep.
it's because I got the same answer, but I didn't do it the same way.
Okay, tell me what you did.
At the first step where we have 1 minus cos squared x, the first one.
Yeah.
Right. I did kind of like a different squared, if that makes sense. So like when I got to like the second step, I had
Well, this one?
yeah, the one beneath it.
This one?
Yeah, where it's written sin squared x.
Mhm.
I had 1 minus cos squared x times 1 plus cos squared x. And I then
No,
divide.
I don't understand. You replace this, instead of writing this, you wrote 1 minus cos squared times 1 plus cos squared?
Yeah,
No, that's not good.
that's not good.
No, because 1 minus cos squared times 1 plus cos squared is 1 minus cos 4,
Okay, yeah, okay.
right?
Yeah. Okay, thank you.
Okay.
For the fourth step,
Yeah.
how is it 0?
Which one? The last step here, this one?
Yeah, that one.
This one here.
Yes.
Why is it 0, you mean? Why is this 0?
Yeah. Yes.
So plug in 0 in the sign. So sine of 0 is 0. And cos of 0 is 1. 1 plus 1 is 2. So 0 divided by 2 is 0.
Okay, thank you.
Okay. Any other questions? Okay, that's good. We have about 15 minutes left to class. So I will try to show you continuity. Okay, so now at this point, you should be able to do in the limits worksheet I sent you, you should be able to do every question there. Okay, if you have an issue with a question, it means that you didn't understand something. Okay, also the web work, you should be able to do everything besides for continuity, but after today's class, you should be able to do everything in the web work. Okay, so let's go. So this is new. Let's go continuity. So here are definitions. A function f is, so it's called continuous at a certain value x equals a if two things are satisfied. Okay, two things. First, the limit as x approaches a of that function has to exist. Okay, exist means from the left and from the right are the same, like we did, you remember, in one-sided limits. Second, the limit as x approaches a of f of x has to equal to f of a, the value of the function. These are the two requirements that I need to have to confirm that a function is continuous at a value a. Okay, I'm going to show you pictures in a minute, and you will see it's going to make much more sense. Okay, so just a second definition: a function f is continuous just continuous. Okay. If it is continuous at all values x in R. Okay, so if for every value of x, the function is continuous, so these two criteria are satisfied, then we say that it is continuous everywhere. Okay, so this means continuous everywhere. This means continuous at a point, at a value. Okay, so let me give you a few pictures, and you're going to see that it's not as hard as it seems. Okay? It always sounds more complicated when I give the formal definition, and when I do a little picture, it becomes very clear. Okay, as you will see. Okay, so let me just represent it here. So let's say this. Okay, so I'm going to draw 4 functions, and for each of these functions, I'm going to analyze the continuity. Okay, see if it satisfies the 2 requirements. Okay. Okay, but that's what I'm doing in a second. So let me draw 4 little functions. Okay, the first one, just move up a bit. Here we go. So the first one is going to be like this. Second one, third one, and the last one. Okay, so here are 4 functions. So they're f, okay, the function. So let's go with the first one. Okay, so they're all, I'm interested in what's going on at A, right, at value A. So first question for function 1. Does the limit exist at x equals A? So I need to verify if the limit exists. Does the limit exist at x equals A? Okay, if yes, tell me why. If no, tell me why. So on the chat, I see already one answer no. that tells me that the limit doesn't exist. So why? Why not?
The limits from the left and from the right are not equal.
Perfect. Okay. So as you see here, if I approach from the left here, I'm approaching this. So I'm approaching here. And if I approach from the right, you see here, from the right, I'm approaching here, and they're not the same. Left and right are not the same. So right away, I could write here that the limit as x approaches a of f of x does not exist. Questions? Okay, so this means already that my first requirement is not satisfied, so this function is definitely not continuous at a. And it's not continuous overall because there's a point where it's not continuous, there's a discontinuity, okay, at x equals a. Second, so I could right away disregard this function. Let's try this one. What about here, the limit as x approaches a of f of x? Does it exist or not? Okay, so it does not exist as well, okay? For the same reason. If I'm approaching from the left, I'm approaching this place. And if I'm approaching from the right, I'm approaching this place, which is not the same place. Okay, it doesn't change anything in my life if this dot is full or not, okay? It doesn't change. I'm just understanding what happens when I'm getting close to this value, close to this point. Whether it's full or empty doesn't change anything. Okay, so again, this function is not continuous at a. Any questions? Okay. This one here. Does the limit as x approaches a exist?
Yes.
Perfect. This one, it exists. Okay, so this is good. Okay, why? Why? Because if you see, if I approach from the left, I'm approaching this dot, which is really close to this dot, this value of y, I mean. And if I approach from the right, here, here, so it's approaching the same place. So the limit exists. Okay, and now the second requirement, so the first is successful. Let's try the second one. So is limit as x approaches a of f of x, is it equal to f of a? Is it?
No.
No, because as you see, right, f of a is here. That's f of a. So not good. Okay, so this fails. It's not equal to. Okay, you understand this little picture that I'm making here? Okay. So this function is also not continuous at a. How about this one here? So limit as x approaches a f of x, does it exist?
Yes.
Yes, we see it. And is it equal to f of a?
Yes.
Yes. So they're both satisfied. This is good, this is good. And so this function is continuous. Okay? Do you understand clearly? It's very important, this.
I don't understand why the f of a isn't is the dot on the third one.
This one here?
Yeah.
Okay, so how do you determine what, when I give you an x, how do you determine what's the f of x? So you stand on the x, in this case in the a, and you look above or below, and you see where where does the graph of the function appear? So here I look down, there's nothing. I look up, I look through this hole, oh, I see right here a dot. So this, at this height, this is my value of y corresponding to this x. That's f of a. That's the image of a. You see it?
Yeah, but if the dot in the f was dark, like filled in,
This?
would that be the f of a? Yeah.
Of course.
Okay.
Very good. And what if they're both filled? What if this is filled and this is filled? What happens?
I don't know.
So what's f of a? Which one is it?
It's not a function anymore.
Very good. Very good. It's not a function. Perfect. That's what I wanted to hear. Okay. So if an x has two images, it's not a function anymore. Okay. It's just a relation, and we're not talking about relations now. We're just talking about functions. Okay. So a special kind of relation, which is a function. Okay. So a function is a relation for which every x has at most one image or one y corresponding to it.
Okay, thank you.
Good. Answers your question? Okay, so let me just give you, so we're going to stop here. We won't have time to do exercises today, but let me just at least give you the definitions while we're here. So this function, so I'm just going to move up here. Okay, so this one here is, of course, continuous. Okay. Now, these three are discontinuous, okay? There's a discontinuity, okay, at x equals a. So the thing is that these two discontinuities are different than this one, because these ones here, in both cases, the function jumps. It goes here, jumps, it goes here. Here, at a jumps, goes here. Here, it doesn't jump. It just skips a point and continues, okay? So these two types of discontinuity are called jump discontinuities. Okay, so here there is a jump, it's called a jump discontinuity at x equals a. Here also, jump discontinuity at x equals a. And this one here has another name. Anybody know it? Those who took the class already? How do you call it? You don't know? Okay, so this is called a removable discontinuity. At x equals a. Okay, so two types of discontinuity, either a jump for these two cases, or removable for this case, or continuous. Okay, good. I got a good question on the chat. Could a function with an asymptote be continuous? So a vertical asymptote for sure not. Okay, because the limit could exist. Okay, I'll go back up here. Okay, the limit could exist. It could be infinity, but it will for sure not be equal to the value of the function, because then that would mean that f of a would have to be infinity, and that means that it's not defined. Okay. Okay, so jump discontinuity, these two, removable discontinuity, these two. This is called removable because it's very easy to get rid of the discontinuity by just moving one point. So I just take this point. If this point wasn't here, but it was at this height, that it would fill the point, the empty dot, then it would be continuous. Okay, so basically continuous means that I could draw the graph without lifting my pen. That's it. And all of these, I have to lift my pen to draw, lift my pen. Here I have to lift my pen to go get this point and come back. Well, here I could just draw without lifting my pen. That makes it continuous. Okay, continuity makes sense even in English. Okay, that's it. We're over time. Okay, so I'm going to take your questions.